Hi, my name is Gopal Goel, and my project is in the mathematical field of random matrix theory. Many problems in the real world can be modeled by matrices, and in many cases, the sizes of the matrices being dealt with can be very large. For example, the energy levels of atomic nuclei can be derived from the Hamiltonian of the system, a matrix from quantum mechanics which describes the underlying dynamics. Now, in the case of heavy radioactive nuclei, the Hamiltonian can be very large and can have many complex factors determining its exact value. So in the 1950s, physicist Eugene Wigner had the insight that one could try to model this Hamiltonian as just a very large matrix with random independent entries. And then he showed that this approximation was indeed accurate and derived theory around this random matrix model. And this result was the original result that spawned the field of random matrix theory. Now, Wigner's original model is known as the Gaussian orthogonal ensemble, or the GOE. My project deals with the generalization of the GOE, known as the beta-Hermite ensemble. One concrete way to visualize the beta-Hermite ensemble is that it models the locations of particles in a charged one-dimensional gas with temperature 1 over beta. And then Wigner's original GOE model is simply the beta equals 1 case of the beta-Hermite ensemble. Now, a natural question about the beta-Hermite ensemble is, what does it look like as the size of the matrix approaches infinity? In 2010, Borodin answered this question for the specific values of beta equals 1 and 2, and he showed that the limiting object was the Gaussian free field, or the GFF. The GFF is a probabilistic field that arises naturally as a limit of random three-dimensional surfaces and is also the main object in the potential theory of quantum gravity, and it has many ties to physics and statistical mechanics. Now, my project is about investigating the strength of this limit, and in particular, does this limit hold when we replace the beta-Hermite ensemble with its discrete derivative, and we replace the Gaussian free field with its sectional derivative? So my project shows that this is indeed the case, and therefore deepens the connection between these two objects. Now, to solve this problem, it suffices to show that the observables of the discrete derivative of the beta-Hermite ensemble converge to the observables of the sectional derivative of the Gaussian free field. Now, by doing some analysis with the GFF, I was able to compute the observables of the sectional derivative of the Gaussian free field, and therefore had a target for what the limit of the observables of the discrete derivative of the beta-Hermite ensemble should be. Now, by using the tridiagonal beta-Hermite matrix model, which allows us to access the beta-Hermite ensemble beyond the classical beta equals 1 and 2 cases, I was able to write those observables as traces of powers of the random matrix, and then in the limit, I was able to expand those as combinatorial sums over paths. And therefore, the problem of showing that the observables match reduced to just a combinatorics problem about these nice paths that show up. And then I solved this combinatorics problem using a very nice couple of bijections. And before I end, I want to mention a few more applications of random matrix theory, and in specifically the beta-Hermite ensemble. It turns out that random matrices can model the noise in raw data, and therefore studying the mathematical properties of random matrices, like my project does, can help us better understand how to separate signal from noise in data from natural phenomenon. Concretely, researchers previously showed that the fluctuations in meteorological data could be modeled with the beta-Hermite ensemble. Now, random matrix theory and the beta-Hermite ensemble have many other applications to fields including telecommunications, finance, number theory, and many more. And therefore, advancing our knowledge in this field could be very helpful for future discovery. Thank you so much.